Well, what's up? More limit laws. Actually, this isn't really a limit law. This is just something, well, it's going to be a big ass proof. You are in no way required to understand what I'm about to do. The only thing you are required to know is the conclusion. And I'm giving you the conclusion at the beginning. The limit as x tends towards 0 of sine of x over x is equal to 1. You can state that at any time you like. You don't have to prove it. You don't have to do anything from here on out. That is just fact. I would get it tattooed on your arm if you can. You need to know this. You're going to need to be able to recognize it, and you're going to just have to state it. It's also true if we were to change the picture and call it, I don't know, let's go with some crazy variable like theta. Well, it doesn't matter if you change the picture that's inside. We're just calling the variable x and then go, no, now we're going to call it theta. It's still frickin' 1. So you're required to know that, but now we're about to go in and do a crazy-ass graphical proof. Now, the design of this proof is to get to this point, which can be solved and done much easier later. It would take me less than 10 seconds to prove that. But this one's going to take about 15 minutes to prove, graphically. But it's going to help us to see a lot of the trigonometry that we have forgotten or never learned. Maybe you're like me that ended up in a calculus class having never really seen any trigonometry. Not my fault. My teacher just decided it wasn't really that important for us to learn, I guess. So many of you are in my same position with the I am. A lot of your teachers are not teaching you trigonometry, or they're just showing you the very, very basics, or making you draw frickin' sine waves, which we never really use again. Well, you might in a physics class. But I'm going to stop ranting and start getting to work. Here we go. I started with a unit circle. Just made a little unit circle right there at 1, 1. All right, so it's got a radius of, what, 1? So let me just, if I just draw something here. There you go. I made a little line. We're going to jump on into this. So this proof is going to kind of come out of nowhere. I don't know how the hell somebody came up with this. Okay? I don't know. I don't know. So inside of our unit circle, so that means that our hypotenuse is 1. Oops, did I say hypotenuse? I meant the radius is 1. All right. And then in trig, oops, that's the wrong one. In trig, we learned that we call that angle theta, right? Coming off of the positive x-axis up to wherever that is. Then what I want to do from this little point, we're going to use this little radius for the whole thing. Now I want to make an area. What I'll do is just make a triangle that comes back down and hits right here at 1, 0. So we have a point here at 1, 0. And then we have a point up here. Does anybody know this point when you're inside the unit circle? And again, I wouldn't have known this. I would not have known this as a calculus student because I didn't learn trig from my trig teachers, well, pre-calculus teachers. But on the unit circle, your x value is always going to be cosine of theta and sine of theta for y. X goes with cosine, y goes with sine, and that's only on the unit circle. Now what we're going to do here is we want to find the area of this circle, or circle. We want to find the area of this. That stuff right there, okay? So we're going to call this one area 1. Now what's the area of this? Area 1. Now that's going to be, it's 1/2 base times height, right? Isn't that how we find the area of a triangle? I mean, we also have 1/2 AB sine C, but that's a different thing. So we have that our first area we're going to look at is 1/2, and what's our base? The base is down here. Oh, that's 1, all right? That's just 1. That's cool. And then what's the height? What's the height? What's the y value? What's the y value? The height is sine of theta. So we found out that our first area is equal to sine of theta over 2. But that's only true here in the first quadrant. If we were in the second, third, or if we were over in the third or the fourth quadrant, we would need an absolute value on that sine of theta. So I just need to pop that in because I only drew it in the first quadrant. It could be in any quadrant. We need to show it's true for anything. All right, neat. So we found our first little area. Cool. We're going to continue to draw bigger and bigger areas here. So I'm going to lose what's in blue right here and say, you know what? Instead of that one, let's look at area 2. In area 2, we're going to make it the whole slice. Not just not just this, right? We're going to have a little bit more. So we're going to have the whole freaking slice. So area 2 is bigger than area 1. All right. So area 1 is, well, it actually could be the same thing. And then we're going to have an area 3 we'll talk about at the end. All right. And it's going to work like that. All right. Cool. Cool. It's just the area of a piece of pizza, or the area of a sector is going to be our area 2. It's area 2. You remember this, right? 1/2. Now what's the area of a sector? Oh no. It's 1/2 r squared theta. That's what it is. That's the area of a sector. You remember that shit. I'm going through this so you can start to remember that there's a bunch of formulas you've forgotten or don't know that are required to be known in this class. So we keep going and we're like, all right, well, what's the radius of the unit circle? I'm pretty sure that's just 1 times the angle. So it looks like we just have theta over 2. But in reality, we really should be saying that that should be the absolute value of theta. You know what I mean? It really should be, because the theta could be negative. So there's our area 2. Cool. And now we're going to go with our third area. We're going to go a little bit bigger. We're going to go a little bit further. So for this one, we're actually going to take this out, remove this point, because we're going to go so much further, and we're going to make ourselves a right triangle here. Dude, who came up with this shit? You know what I mean? Like, ooh, a little too far there. Who came up with that? Who had this much time on their hands to figure this shit out? All right, so here's our area 3. All right, now I can kind of do one of these. There's our area. We're going to take that whole big bad boy right there. And let's go find, what's that area 3? Area 3 is, so it's 1/2 base times height is a triangle, right? So the base is 1. Okay, we're good there. Now what's that height? What's this value? What's our y value? Well, the way we're going to go find this thing, is let's go trig. So we don't know what the hypotenuse of this thing is, right? Of this green right triangle, this shitty triangle I have scribbled in there. We don't have the hypotenuse, but we do know the adjacent, and we want to know the opposite. Adjacents and opposites. So tangent of theta is the opposite over the adjacent, right? So that's y over 1. Oh shit, our y value is just 1. Oh shit, the height is just tangent. Oh no, there it is. So we could actually say the area 3 is just tangent of theta over 2. But tangent can be negative, so let's slap an absolute value on it. Well, there we go. There's the beginning. We're done with that freaking little circle and the triangle games. We've gone through. We talked a little bit about trig. But we're going to now set this thing up saying that our first area, the absolute value of sine of theta over 2, is less than or equal to the absolute value of theta over 2. Sorry that my Surface sucks so bad that it changes my handwriting. Yeah, you should really go buy one of those things. They're wonderful for $1,000, and they don't actually work like they say they're going to. It's great. It's good stuff. Okay. So we're going to use those 3 different areas we found, knowing that one is bigger than the other is bigger than the other. And now we're going to do some fancy algebra to go improve our little statement here. Okay. So let's multiply everything by 2 right off the bat. And we're going to say the absolute value of sine of theta is less than or equal to the absolute value of theta, which is absolute. Okay. Now, let's keep going. Now let's write in tangent differently, because you know what? Tangent? Come on, yo. There's no such thing as tangent. There's only sine and cosine. Anytime you're tripped up and you're seeing a tangent, change it. You see a secant, change it. See a cosecant, change it. See a cotangent, change it. There's only sine or cosine. All right, so we get to this point. Now, what can we do? Where can we go? Well, I think, since there's a sine and a sine, let's multiply everything, or actually let's divide everything by the absolute value of sine of theta. Okay, just like this. And we're doing this so we can get shit to go. Goes away. Okay? We multiplied by 1 there. So what are we left with over here? We get 1 is less than or equal to the absolute value of theta, or the absolute value of sine of theta, which is less than or equal to. Those went away, and we get 1 over the absolute value of cosine of theta. There goes my corrupted screen. Okay. Now, quick question. 1 is greater than a half, is greater than a third, is greater than a fourth, right? You believe me there. All right, now let's flip it all over. Let's reciprocal everything. 2, 3, and 4. What's bigger? Right? Well, of course. So the point is, when you hit something with this reciprocal, you're actually going to change the direction as to what your less than and equal to signs are going to be. So let us flip everything over. And here we go. We just won't change them to their reciprocals by flipping them on over. And then once we flip them on over, we're going to change our inequalities. Now there are a bunch of domain issues, and there's a reason why I can actually jump to this next step and do this. I'm not going to go through and explain all of it, because that would take about as long as just doing the whole proof. That this is true just for the fact that sine of theta is an odd function, theta is an odd function, cosine is an even function, making it to where there's an even function. None of this is going to need it. So there's my quick way of saying why I can lose them. This is a proof. You're not required to understand. You just have to know the output. All right, now once we're here, we can now see we have that sine of theta over theta. This is actually what I've been trying to get to. So let's hit everything with a limit. And I'm doing something that's well before I've even given you the theorem. So the limit, and let's take theta and let's send it to 0 for all 3 of these pieces of 1. And then let's take the limit as theta goes to 0 of sine of theta over theta. And then let's look at the limit as theta goes to 0 for our last piece, just our cosine of theta. Again, I'm sorry about my corrupted screen. I do have a little arthritis, but my hands aren't that shaky. So what is our first limit? The limit is theta goes to 0 of 1. Remember that constant rule we had that says it doesn't really matter if it's just a constant, just write down the freaking answer? And you're like, dude. This is just 1. And then let's write this back in. Our sine of theta over theta. Because we don't know what that one is. If we knew, we would have just solved it right at the beginning. But this last one, we can just plug our number in. So we know cosine of 0. It equals 1. Okay, so we just found out that the limit of theta the limit of sine of theta over theta as theta goes to 0 is greater than or equal to 1, and it's also less than or equal to 1. So I wonder what it could possibly equal. Do we need a theorem? Do we need a theorem to tell us that it's equal to 1? I think by no shit. The limit as theta goes to 0 of sine of theta over theta is equal to 1. I don't think we need a frickin' theorem oh, really? It's trapped between 1 and 1. I wonder what the hell it could possibly be. But what this is called the squeeze theorem. It's called our squeeze theorem. And I'm going to quickly write this thing out. And it's just saying that if f of x is less than or equal to g of x, which is less than or equal to h of x, a couple functions, when x is near a, then, and we have that the limits, as x tends towards a, of the outer ones. The outer ones are, if those two are equal to each other, the outer ones equal some frickin' limit, then, by the old no shit theorem, back here saying that, hey, you got the same frickin' limits on the outside, I wonder what the limit in the frickin' middle might be. Then, that limit, the limit as x tends towards a of the center function, that center function is no shit. It goes to the same damn number the other one went to. This is what we call the squeeze theorem. All right, so we'll come back. Squeeze theorem. I'll have it professionally written out for you in the next one. We'll mess around with a couple of problems, but I do this proof so we can talk about the squeeze theorem and we can talk about all that different trig shit that you forgot. I'm going to say that most of you will not understand hardly a word I just went through. You'll know sines, you'll know tangents, you'll know cosines, but this is a lot. It's a little too much too soon, just like 2.4, your next session. So do your best and I will see you in the next one. Sorry for such a long video.